Thank you for the introduction. Hello, my name is Aaron Heineman, the Inorganic Product Line Leader for PerkinElmer. In today's talk, I will discuss how we improve the specificity of a Tandem ICP-MS spectrometer by using a quadrupole-based reaction cell. During this talk, we will go over the history of ICP-MS, what types of interferences we experience in ICP-MS, what are the spectral interferences, how we control interferences in ICP-MS, and we'll talk about cell technology, the history of cell technology, what is a collision cell, what is a reaction cell, and then we'll discuss what is the difference between that and a dynamic reaction cell. And finally, we'll get into how we improve specificity with a quadrupole-based reaction cell. First, I would like to give you an overview of PerkinElmer ICP-MS history. PerkinElmer has a proud pedigree of innovation, beginning with the Elan 250 as the first commercial ICP-MS. The Elan series has had a variety of innovative additions to the series when in 1999 the dynamic reaction cell was released. In 2010 the NexION series was introduced, leading us to 2017 with the NexION 1000 and 2000 systems. The Elan platform that included models from 250 to the 9000 dominated the ICP-MS market for many years. Several innovations like turbomolecular vacuum pumps, the free-running generator, new optics, dual-mode detector, and the dynamic reaction cell were incorporated in these instruments. The DRC was truly a breakthrough in the reduction of spectral interferences and lowering detection limits. A new chapter of PerkinElmer ICP-MS instruments was launched in 2010 by the introduction of the NexION 300. It was a benchtop unit with a quadrupole ion deflector, triple cone interface, an auto XYZ stage, and new synergistic software. These design changes led to an instrument with much higher sensitivity and lower backgrounds. In 2017, the NexION 2000 was released, this time boasting an extremely small footprint, a new solid-state RF generator, and a new load coil design. The NexION 1000 was released a year later. During the NexION generation instruments, new application innovations were released with nano and single-cell capabilities and software packages that were supported by the fast scanning capabilities of the NexION platform. These, along with many other innovations, have kept PerkinElmer at the forefront of application advances. And now, in 2020, we are proud to add to the NexION series of ICP-MS the NexION 5000 Multi-Quadrupole ICP-MS. Over the history of ICP-MS, PerkinElmer has had many innovative hardware patents. Here's a partial listing of them. Okay, so when the first commercial ICP-MS system was introduced in 1983, it was of general opinion that this new technology freed analysts from worries about interferences. Now, many years later, we know that interferences do exist in ICP-MS, but we have a pretty good understanding of them. Over the years, new techniques and technologies have been developed to reduce or eliminate them. There are several types of interferences in routine ICP-MS analysis: physical, matrix or plasma loading and ion sampling effects, and spectral or isobaric and polyatomic interferences. Physical interferences are generally related to the sample's viscosity and surface tension, affecting their transport through the tubing, nebulizer, and spray chamber. Due to the presence of sample matrix, an analyte signal can be suppressed or enhanced in comparison with standards without matrix, resulting in incorrect analytical answers. Matrix matching of calibration standards and the use of internal standards are common techniques to compensate for these types of interferences. Matrix interferences can be defined on how the matrix affects the energy of the plasma and what happens when the sample enters the vacuum system, which are known as space charge effects. One form of matrix interference is related to changes in the ionization efficiency of the analyte in the plasma. Samples with high total dissolved solids or organic matrix samples can lower the energy of the plasma as a whole and decrease the yield of ionization, affecting sensitivity in comparison with non-matrix standards. Plasma loading effects are compensated by internal standards, using hot plasma conditions, and generally lowering the nebulizer flow or lowering the amount of material entering the plasma. Spectral interferences, both isobaric and polyatomic, are caused by other ionic species having the same or very similar mass to an analyte. In quadrupole-based instruments, which operate at approximately 1 atomic mass unit, means a direct overlap of an interference on an element of interest. In this presentation, we'll discuss how mass spectrometer design and cell technologies are employed to mitigate these issues. Here is another way to view interferences. They can be broken down to either spectroscopic or non-spectroscopic. The spectroscopic interferences can be further broken down to isobaric and polyatomic interferences. Non-spectroscopic interferences can be then broken down into matrix effects in the plasma and space charge effects in the mass spectrometer. So when the ions enter into the vacuum of the mass spectrometer, they can be affected by adjacent ions. This is called space charge effect. Behind the cones, the plasma changes into an ion stream due to the loss of electrons. Since ions have a positive charge, heavy ions repel lighter ions, causing mass-dependent matrix effects, where lower mass ions are affected more. One way that we can combat space charge is by the use of a triple cone interface, or TCI. The triple cone interface provides a 3-step reduction in pressure between the plasma, which is at atmospheric pressure, and the vacuum in the mass spectrometer, resulting in a substantial reduction in the divergence of the ion beam, and thus reducing the space charge effects. In the NexION 5000 ICP-MS, this was taken a step further, and the hyperskimmer, the third cone in the triple cone interface, was adapted with a ring lens. This patented hyperskimmer omni-ring assembly reduces the space charge effects even further by focusing the ion beam into the quadrupole ion deflector of the NexION mass spectrometer. Another way we can reduce matrix effects is by using gas dilution. Leveraging AMS, or all-matrix solution, the user can introduce a flow of argon into the neck of the spray chamber via the AMS port to dilute and dry the aerosol stream. AMS has a predictable response across the mass range and reduces the amount of matrix reaching the plasma, lowers the level of oxides, and allows for more efficient ionization due to the enhanced plasma robustness. So what are isobaric interferences? Isobaric interferences happen when there are naturally occurring isotopes for more than one element at the same mass, or it can happen when a doubly charged ion occurs at half its mass. At some mass numbers, there are naturally occurring isotopes for more than one element. If possible, we would like to choose an alternative non-interfered analyte isotopes for analysis. In the top right example, you can see at mass 50 and 138, 3 different elements have isotopes at those masses. In the percent abundance excerpt below, you can see that every isotope of cadmium has a tin overlap except for mass 113. And what are polyatomic interferences? Polyatomic interferences happen when elements present in a matrix combine with each other or with plasma gases, forming molecular ions at the same mass as an analyte of interest. The most common polyatomic ions are argides, oxides, hydrides, hydroxides, and dimers. Listed here are some common molecular interferences. Most of these are predictable and come from known elements. Here is an example of major polyatomic interferences generated when the matrix contains nitrogen, sulfur, chloride, carbon, calcium, and sodium. As you can see, many of the first row transition metals and the metalloids are significantly affected. So, if we look at all the ways to combat interferences, you will see that there are sample introduction modifications that can be used to reduce physical and matrix effects, such as desolvation techniques, mixed gas plasmas, dry plasmas, cold plasma conditions, etc. Also, historically, prior to collision cells, elemental equations were used to correct for spectral interferences when no interference-free isotopes of the analyte could be found. That approach had many limitations and could lead to incorrect results. Then came cell-based techniques to reduce your spectral interferences. The first commercial use of a pressurized cell was in the form of a hexapole collision cell, reported by Turner et al. In 1997 and commercialized by Micromass as the platform. Subsequent commercial systems was the PerkinElmer Elan DRC, the Thermo Elemental PQXL, and the Agilent 7500C. So, what is a collision cell? Well, a collision cell originated in tandem quadrupole organic mass spectrometry for collisional induced dissociation, or CID. The purpose of collisional induced dissociation was to induce fragmentation of parent molecular ions into daughter molecular ions for subsequent mass analysis. However, the collision energy required to successfully fragment many metal polyatomic ions exceeds the difference in the ionization potentials of the isobaric atom and the reaction gas. Therefore, CID is a relatively ineffective process for ICP-MS. So, kinetic energy discrimination. All interactions of ions with molecules are collisional processes. However, for the purpose of removing interferences in ICP-MS, collision cell technology takes advantage of kinetic energy discrimination, or KED, in which we introduce a non-reactive gas, such as helium or xenon. Okay? In a collision cell, the ions entering the cell will all have the same kinetic energy coming in. As the ions transit through the pressurized cell, they will collide with the gas in the cell. As collisions occur, the ions will lose kinetic energy in the axial direction. As the ions are exiting the cell, they can then be discriminated against by the application of a potential hill or energy barrier downstream of the collision cell exit. This is typically accomplished by making the DC rod offset of the collision cell slightly more negative than that of the mass filter. The amount of energy an ion will have as they exit the cell will depend on the mass of the ion and the gas, the collisional cross-section of the ion, the cell pressure or gas thickness, and the distance the ions have to travel. Kinetic energy discrimination, interference removal, is independent of the matrix and is applicable in a variety of applications where reaction gases cannot be found or really adequate levels of interference removal is achieved by KED alone. However, note that for monoatomic, doubly charged, and many polyatomic ions, this method is not as effective in the removal of interference as is reaction cell technology. Another drawback of collision mode is a significant loss of analyte sensitivity, especially at lower masses due to scatter loss. Therefore, generally, collision mode can be applicable for semi-quantitative analysis, environmental monitoring, and any analysis without the need for ultra-low BECs and detection limits. The effect of KED can be best characterized by the amount of interference and the difference between the size of the interferent and the analyte. If the size differential is large, the effect is more pronounced. as in the example here of arsenic and argon chloride. If the size differential is small, the effect may not be as effective and may require a higher flow, as in the example here of vanadium and ClO. If the analyte is larger than the interferent, KED will just not work. A good example is with calcium and argon. What is a reaction cell? In the simplest terms, a reaction cell is a pressurized multipole cell where ion molecule reactions occur. Reaction cells take advantage of exothermic reaction conditions based on the reaction thermodynamic properties of the ion and molecule in the system. In basic terms, if the enthalpy of the ion molecule is negative, then the reaction is exothermic and might proceed. If the enthalpy of the reaction is positive, then the reaction is endothermic and will not take place unless additional energy is contributed to the process. In a reaction cell, this addition of energy can be contributed by excess axial kinetic energy or by the RF applied in the cell. On this slide, we list a few advantageous reaction chemistries used in reaction cells due to either the analyte gas or the interference gas reactions proceeding, but not the other. An interesting note that in the past, when collision cells such as hexapoles and octopoles were used to promote these ion molecule reactions, they were called things like molecule ion reactors or ion guides, beam guides, reaction chambers. Then came the dynamic reaction cell. The dynamic reaction cell, or DRC, is an enclosed mass filter quadrupole array which can be pressurized with a reactive gas. The array uses 4 conductive rods powered by a frequency scanning power supply, which is synchronized with the analyzer quadrupole. When the DRC is pressurized, it provides online chemical modification of the ion beam to reduce interferences. The DRC employs a chemical bandpass technique, which controls the extent of competing reactions, which may contribute to the chemical background. As stated on previous slide, pressurization of the cell with a reaction gas permits the conversion of one isobar to a different ion which does not interfere. It can also be used to convert an analyte into a polyatomic ion at a mass where no interference is present. The specific chemistry is the reaction is dependent on the nature and density of the reaction gas and the electrical fields within the cell. The user can control the fields within the cell for the desired effects and to limit undesired side reactions before products enter the analyzer quadrupole. Another benefit controlling the gas flow and DRC-RF applied to the DRC is thermalization. To thermalize the ion beam means to redistribute the energy spread of the ions, essentially. Thermalization, in the case of an ion beam injected into a pressurized cell, is achieved with the buffer gas, or the reaction gas, under certain thermal conditions. And closer to a thermal equilibrium the ion beam becomes, the more efficient the reaction will be, and therefore more effectively removing interferences. So, under reactive conditions, sequential reaction chemistry is to be expected, with the production of intermediate product ions of various masses. Each product ion has the potential to interfere at the mass of some other analyte ion. So in the example here, when we're trying to determine vanadium in the presence of chloride, Q0 will initially remove some ions. Q1 will then filter all other ions not equal to a mass-to-charge ratio of 51. And the remaining ions entering the universal cell, or Q2, are vanadium and ClO. In the case of pressurization with pure ammonia, or as pure as you can get ammonia, the ClO is removed by reacting with ammonia via charge transfer. However, through a sequence of further chemical reactions, intermediate ions could be produced that again interfere at mass 51. Examples are shown here in red at the bottom. So when you're not using a quadrupole-based cell, all these reaction byproducts, these intermediate ions, will be retained within the cell. However, in the case of a quadrupole-based cell, one of the intermediate ions or reaction byproducts, if it has a mass that falls below the stability cutoff, the well-defined stability cutoff of the quadrupole, will be ejected from the cell. And further reaction, potentially producing new interfering ions, will be suppressed, as in the case of the chloride and ammonia ions shown here in the pink. Another source of intermediate ions or unwanted ions is due to impurities in the reaction gas. Even with the best gas supplies as possible, that trace levels of organic impurities will be present in the cell or could be present in the cell. Again, having a quadrupole inside the reaction cell will allow for the ejection of any intermediate ions, creating these interferences due to this, impurities in the gas. Clearly, the quadrupole offers substantial control over these sequential chemistries by allowing the selection of conditions, RF amplitude and frequency, that provide an adjustable and well-defined mass cutoff. So in summary, a collision cell versus reaction cell versus dynamic reaction cell, all are multiple devices within a cell that are pressurized with gas. Collision cells solely utilize KED to filter unwanted ions. They use a kinetic energy discrimination. That really is a distinguishing characteristic of collision cell operation. Reaction cells use reactive gases to promote ion molecular reactions to chemically resolve these interferences. This is, again, one of the major distinctions between collision cells and reaction cells. However, over time, the difference was blurred or confused by various manufacturers and researchers. The distinguishing characteristic that appears to have been overlooked is that reaction cell was intuitively understood to involve thermal chemistry, or at least near thermal conditions, so that reactions are governed by the thermochemical properties of the ions in reaction gas. The introduction of the dynamic reaction cell, where a quadrupole is used, typically operate with relatively heavy reaction gases such as ammonia, methane, oxygen, or other at pressures that provide thermal conditions. Discrimination against ions produced within the cell is preferably accomplished by establishing the appropriate mass bandpass and not by using kinetic energy discrimination. Big breakthrough in dealing with spectral interferences came with the incorporation of universal cell technology into ICP-MS spectrometers. The universal cell can perform two different tasks depending on the nature of the introduced gases and electrical parameters of the cell. The first one is having a cell that acts as a dynamic reaction cell with reactive gases. The second is by using the cell as a collisional device, employing kinetic energy discrimination with non-reactive gases. With the NexION series of instruments, they're the only instruments that have the universal cell technology offering KED and true reaction cell capabilities. In general, KED mode reduces polyatomic interferences, fairly simple, doesn't need much optimization. However, when we're really trying to get ultimate detection limits for area interfered isotopes, dynamic reaction cell has proven to perform. Utilizing all three modes and utilizing newer, latest technology of ICP-MS allows for data confirmation. The software automatically handles any mode switching. So, here's a scanning quadrupole and our universal cell. We need to first highlight the key difference between this and other cells is that the scanning quadrupole is there. That scanning quadrupole, as I said, can create a finite bandpass instantly, and it's dynamic, so it's scanning with the analyzer quadrupole. Note, it can be operated in KED mode or reaction mode. The converse is not true. A multipole, hexapole, or octapole cannot become a quadrupole. These devices are passive ion guides because they do one thing, and that's guide ions through cells. So universal cell technology in summary: standard mode, we have no gas in the cell. KD mode, we have an inert gas, and we have kinetic energy discrimination. And in DRC mode, we eliminate most challenging interferences using pure reaction gases and employing dynamic bandpass. One more lesser known capability of the universal cell is extended dynamic range, or EDR. This powerful capability of the cell enables the analyst to use the quadrupole to detune the sensitivity at a specific mass for high concentration elements so that they can be analyzed together, the same run, in the same test tube solution of sample, with very low concentration elements. Even though that concentration exceeds the dynamic range of the detector. The table on the right of this slide shows the equivalent electronic dilution achieved with increasing the electronic settings of the universal cell, the RPAA. The graph shows the resulting peak of sodium after applying EDR, or equivalent to 1 to 10 dilution of only sodium in the sample. All other masses are not affected. Now, introducing the NexION 5000 ICP-MS, beyond triple quad. So when we went to produce the NexION 5000 ICP-MS, we had to ask our customers, what challenges do you face? Many customers need to go lower and lower in concentration, and pushing detection limits even lower for their sample types. Another key concern is accuracy, data accuracy, ensuring the data that they're producing on a day-to-day basis is accurate, and they're confident in that. And then productivity. So reduction of downtime improves the production in the lab. Another big concern. The NexION 5000, our multi-quadrupole ICP-MS spectrometer, has 4 quadrupoles, enhanced sensitivity, lower BECs than the predecessors, and now contains channels for 4 gas cells using pure gases or gas mixtures. Or if you don't want to buy gas mixtures, which can be expensive, you can do on-the-fly gas mixing. NexION 5000, there's a diagram of the ion path. Our Q0, or quadrupole ion deflector, filters neutrals and photons while focusing a specific mass into Q1. Q1 is the first analyzer quadrupole that controls the ions entering the universal cell. Universal cell, Q2, fully controls the reaction and controls what leaves the cell. And then Q3, the last analyzer quadrupole that controls what hits the detector. Here's a comparison between single quad and our multi-quad ICP-MS. So the NexION 1000, 2000 series and the NexION 5000. You can see here we've added an additional quadrupole to the system. In addition, note that the quadrupole function is the same for the quadrupole in the NexION 2000 as in Q1 and in Q3 on the NexION 5000. We have a mass range of 2 to 285 AMU. We can go down to 0.3 AMU resolution, but typically operate at about 0.7 AMU on both analyzer quads. Based on the needs of our customers, we ensured during development of this product that the key benefits that it provided to our customers was accuracy, detection, throughput, and productivity. As I said, all key requests and needs from our customers. Here's a list of NexION 5000 acquisition modes. So we can run it in single quad mode, MS-MS mode, mass shift mode, precursor ion scan mode, product ion scan mode, or we could scan individual quadrupoles and the other quadrupole as an RF-only guide. In Q2, we can not add gas, we could add a collision gas, or more typically in this sort of system, add a reaction gas. So, if you're going from a single quad system to this, you can run your methods and your routine methods as a single quad. Whereas Q1 or Q3 is the resolving, and the other is an RF-only guide. You can also run your reaction or collision methodology in this system just as you would in the past. Now, for better data confirmation, greater accuracy, we can get into MS-MS mode, where both quadrupoles are resolving, or mass shift mode, where we're using a reaction gas in the cell and reacting the ions coming out of Q1 to another mass and analyzing them there using Q3. What we can do for method development is we can do precursor ion scans, where we're setting Q3 to a specific mass, and we're scanning Q1. Or, more commonly, we can do a product ion scan, where we set Q1 to a specific mass, we let a specific mass react in the cell, and then scan Q3 to see what it produces. Some of the key things when we were developing the NexION 5000 was ensuring we had high accuracy at low concentrations, keeping those BECs low, keeping the background low for customers who are trying to drive to zero, and being able to do that in complex samples. So some of the features that allow the system to do that is the free-running RF generator that came from the NexION 2000. This free-running RF generator is very robust and very responsive. Within one method, you can be running hot and cold plasma conditions. Our cones have a very wide aperture compared to other cones on the market, and that allows for reduction in occlusion or blockage of those cones. Again, longer stability, system runs longer, less maintenance, greater productivity. EDR, super powerful. If you're doing laser ablation and have very high matrix components you want to monitor, or you're looking at your majors in a particular chemical or sample type, and you want to look at trace elements at the same time, you use EDR. You just use EDR. EDR also reduces the ion hit on your detector. Your detector lasts longer. And then we also have AMS to allow for up to a 200 type dilution. Another key design thing of the NexION series is low maintenance. No lenses to clean or maintain. Right? Once you're in the mass spectrometer, there's nothing you're cleaning or maintaining. The Lumicoil technology, no cooling required. It's a solid piece of aluminum, cools fine. All by itself passively with the exhaust. So very easy to maintain. And then ease of use. There's some significant improvements for ease of use. Since the introduction of ICP-MS, the semiconductor industry embraced ICP-MS techniques for measuring contaminants due to its sensitivity and selectivity. The need to monitor contamination at very trace levels. Recently, also, single particle ICP-MS is used for screening particle contamination in these high purity chemicals. So one of the goals in developing the NexION 5000, as I said, was the ultimate in BECs, the lowest background equivalent concentrations and detection limits in a variety of matrices. So, let's look at a few applications of the 5000 in the semi industry where low BECs and DLs are crucial. So, in this case, is an example of are detection limits. Some have detection limits attained in ultra-pure water. The latest semi-guide for ultra-pure water used in the semiconductor processes requires DLs or performance to be lower than 1 part per trillion for 26 elements essential for the semi-industry. That's that red dotted line. The NexION 5000 detection limits for these elements and many others are below 0.3 parts per trillion, which is much lower than the current specification. So another thing, if we compare detection limits for ultra-pure water obtained in hot plasma condition, indicated by the blue bars on this graph, and detection limits in cold plasma, indicated by the red bars on this graph, we can see that detection limits in cold plasma are even lower. And in this case, they're all below 30 parts per quadrillion. Okay, so cold plasma mode is definitely applicable, for elements that have argon-based interferences, argon and argon-based interferences, or whose sensitivity is enhanced by the reduction of argon ions in the plasma beam, usually lower mass, lighter mass ions. The universal cell and dynamic bandpass tuning really produces reliable and repeatable cluster formation. As in the case of titanium. Titanium is significantly interfered with, as you can see the list of interferences there, especially its most abundant isotope at mass 48. Therefore, titanium is readily determined in mass shift mode as a cluster. Okay, and with NexION 5000, our ability to use 100% pure ammonia, we can control those reactions. We can really guide that reaction to an ammonia cluster. And typically, as you see on this chart, we run it at about mass 131. So we react titanium from mass 48, most abundant isotope, up to 141. However, with the universal cell, we can play with the flow rate of the gas, and we can modify RPQ on the system to really optimize reaction chemistries. In this case, you'll see it's optimized, and the reaction chemistry here is 131. So that's really a step beyond traditional quadrupole ICP-MS. Being able to use dynamic bandpass tuning to a quadrupole inside the cell, another quadrupole in the cell, allowing us to really hone in and deal with these interference and potential secondary reaction chemistries. Here's some data from calibration in sulfuric acid. So some calibration curves and the determination of titanium and sulfuric acid. And you can see here what we've done is we have calibration curves for mass 131, so the cluster at 131, and the cluster at 114. There's another cluster of titanium and ammonia at 114. You'll see they're sub 1 ppt for both, but you'll see for mass 131, a BEC of less than about 0.2, less than 0.3, and a detection limit of less than 0.1 part per trillion in 10% sulfuric acid. So it is just a 1 to 10 dilution of sulfuric acid. There's a lot of sulfur in there, and so that's quite impressive. Another exceptional performance actually in sulfuric acid, one of the more difficult ones, even more difficult than titanium if you can believe it, is zinc. Zinc is very difficult in a sulfuric acid matrix. So by using the pure ammonia, we're able to produce a very reproducible cluster at mass 115. We can move zinc up to 115 from 64. And as you see here, we're getting BCs of a half part per trillion. And again, less than 0.1 part per trillion detection limit. As the example I showed earlier, the example of interference-free analysis of vanadium in the presence of chloride, right? Only a system with dynamic reaction cell can really ensure that you're preventing the formation of undesired species. These unwanted intermediate ions or reaction byproducts. Another way of analyzing titanium or arsenic is by using oxygen. So we can actually do the mass shift with oxygen and move our arsenic up to mass 91. In the case of titanium, we could move mass 48 to mass 66. And of course, the quadrupoles are set at about 0.7 AMU. Another application is ultra high purity HCl, hydrochloric acid. So we did a study, a hydrochloric acid test, and you can see here, this is a test measuring 48 elements, measuring a standard of 50 part per trillion spike into 20% HCl, 1 to 5 dilution of HCl, and analyzing that over 6 hours. RSDs are all less than 4% for all these elements. And drift is less than 15%. So excellent long-term stability in a very harsh matrix. This is just taking concentrated HCl and diluting it 5 times. And in that solution of 20% HCl, here you can see vanadium and chrome, right? Vanadium, as we've discussed, at mass 51 has CLO interference. Okay, and chrome has ClOH, or hydroxide formation. Both using ammonia, we can really reduce those BCs, really bring the background down at these masses. So here's the calibration of vanadium and chrome in 20% HCl. BC of vanadium is 0.03 in this matrix, and in chrome it's 0.17, 0.18. So BC with both with detection limits of 0.02 ppt. So in 20% HCl is a very good result. Those of you who are not in the semiconductor area, we also done a lot of work in biomonitoring or clinical type of analyses. And we've been running a lot of bloods and urines and so forth and getting some excellent results. Again, getting more confidence at that lower range. Having more confidence in the accuracy of the data with the NexION 5000. We can run in all these different modes with various reaction gases at a variety of settings if you want to confirm your data. And with a multi-quadrupole ICP-MS with two analyzer quadrupoles that normally operate at about 0.7 AMU, you can see that in blood, where we have very high levels of iron with relatively much lower levels of manganese, so whole blood has about 500 part per million of iron and maybe about 10 part per billion of manganese. Red blood cells even higher iron. Okay, so you can see that even with these high iron concentrations at mass 54 and 56, we have practically baseline resolution. We're using ammonia as a reaction gas, and this is in MS-MS mode. So both quadrupoles are resolving. So again, very powerful solution for resolution of these big interferences. Traditionally, you would see a big overlap from mass 56. Even with ammonia, with reducing some of the polyatomics, there would be still a bit of an overlap from from mass 56. So here we're getting baseline resolution on the manganese. I just wanted to kind of just remind everyone what the IUPAC definition is of a triple quadrupole mass spectrometer. So it is a tandem mass spectrometer comprising of two transmission quadrupoles in series with a non-resolving RF-only quadrupole between them to act as a collision cell. Okay, we went over collision and reaction cells. Remember, the quadrupole in the next in series universal cell applies a band path. Therefore, it's beyond a triple quadrupole. Another thing I want to just point out, there's some misinformation put out in the world, and we're seeing some statements from various people putting these sort of comments out there, and I just want to address these. In the first statement, it's actually incorrect. The first generation of cell systems I discussed earlier were not quadrupoles, they're actually hexapole and octupole-based. And the first one being the micromass platform, right? And even the Agilent 7500C. Another strange thing in these comments is constantly referring to their cell as a collision cell. However, in Tandem ICP-MS, and you actually don't want to use a collision cell to eliminate interference. You don't want to use kinetic energy discrimination. You want to use reaction. So it makes sense to have a reaction cell and a quadrupole mass filter, as we discussed earlier, not a collision cell. And the other statement on effectively transmitting ions without losing sensitivity, collision cell needs a large ion stability region. Hexapole or octupole collision cell affords larger ion stability. Yes, this is true, it does, as a static device. But what's being omitted is that a DRC, a quadrupole cell, has the ability to do mass filtering, therefore removing reaction byproducts. And the quadrupole has the ability to be dynamically varied. It's dynamic, hence the word dynamic. So it's dynamically varied for optimal mass transmission. And if you want, optional attenuation, the extended dynamic range. So remember, the performance of a system over the whole mass spectrometer to transmit ions as a whole is not solely dependent on the cell. Now, and although there is a stability region, a good stability region during the brief transit through the cell, the transitions when going from quadrupole to octupole do cause ion beam destabilization issues. So please take some of those things into account. All right. Well, in summary, we've discussed, interferences in ICP-MS, what collision cells, reaction cells are, what's a dynamic reaction cell, what makes it dynamic. Okay, and then I've gone over the NexION 5000 multi-quadrupole and why it's beyond triple quadrupole. And just wanted to remind everyone of the entire atomic spectroscopy portfolio. PerkinElmer is not just an innovator and leader in ICP-MS, but we also have AA and ICP as well. So here's the PerkinElmer family of inorganic instruments. So starting on our left with our Pinacle series Flame AA, Pinacle 500, and our Pinacle 900, which is a stacked flame furnace. Avio series ICP-OES, the Avio 200 and the Avio 500, and our well-rounded ICP-MS offering, the NexION series. And now we can take some questions. Thank you.